Currently we've got two TBMs underground, Joan and Meg, TBM number 1 and TBM number 2. So what you see here is the machines arrive on site to the surface. Part of the machines are assembled on site, but the main parts of the components are then assembled underground, including the cutter head, which is the last and final piece that is installed onto the TBM before tunnelling operations commence. In the next couple of weeks, TBM number 1, Joan, will be successfully launched and will commence her journey towards South Kensington. The tunnel drive lengths towards South Kensington are just over 1,000 metres, so just over 1 kilometre. TBM number 2, Meg, she'll start about 1 month afterwards. So we'll have 2 concurrent TBM operations heading towards South Kensington. Concurrently, as the TBMs are making their way towards South Kensington, the cruiser will continue to build the station structure. What you can't see behind me right now, but at the bottom of the station structure are concrete slabs and some of the concrete walls that have already been concreted. So again, as the tunnelling works proceed, both the station structure will continue. Once the TBMs have arrived at South Kensington, they'll be recovered through a shaft, and some of the TBM components will be extracted back down the tunnel, back here to North Melbourne Station, and relocated to the east end of North Melbourne Station box. Again, we've got a repeat process then in terms of setting up both TBMs and actually commencing their tunnelling journey towards Parkville Station. Parkville Station to the east of us is just over 1,000 metres in tunnelling length, and those machines will probably start early next year sometime, their journey towards Parkville Station. When they do arrive at Parkville Station, they will not be extracted, they will actually travel through Parkville Station and then continue their journey towards CBD North. All of the time that the tunnel machines are working towards Parkville and working towards CBD North Station, North Melbourne Station continues to provide those support services for the TBMs. So what sort of support services are we talking about? Well, we're going to have segments being brought in from Deer Park. The segments are individual concrete precast segments, and they form what we call a ring. A ring length is about 1.7 metres long, and each ring contains 6 individual segments. They all account to about 25 tonnes in weight. These concrete segment rings are installed within the TBM as the TBM progresses. So basically the TBM advances with an excavation cycle, the concrete ring is then installed within the TBM, and the process is repeated again. So TBM number 1, Joan, the cutter head has been successfully installed onto the front end of the machine, and the pressurized steel bell is in position. The pressurized steel bell is a very important component of the tunnelling operations, as it does provide an environment where pressure can be applied to the TBM, and this pressure is necessary to make sure that as the TBM breaks through the diaphragm wall, that the ground behind the wall and the groundwater stability is maintained and controlled. So the temporary steel bell does avoid the use of temporary grout blocks behind the diaphragm wall area, which again is a very efficient way and means of ensuring stability during the initial TBM launch and the initial TBM boring, which is quite a critical aspect of the tunnelling operations. The Tbm Cutter Head itself weighs more than 100 tonne, and the shield is comprised of 3 individual components, where you have the main bearing, you have the drive motors, you have the segment erector, you have the TBM operators cabins, and you have the pumps that are required for the slurry operations. The TBM shield itself is approximately 15 metres long, and when it's all assembled and put together in one piece, probably weighs more, about 800 to 900 tonnes. Behind the TBM we have what we call the Tbm Support Countries, which are individual steel structures which contain all the support elements required for TBM operations. These include refuge chambers, emergency refuge chambers, the transformer packs, crib facilities, welfare facilities for the tunnelling crews, and also houses some of the components that are required to perform the TBM tunnelling operations. During TBM operations, it is quite normal practice for the TBM to stop excavation and for maintenance crews to go out to the front of the TBM and to the cutter head and to check for wear and tear on the cutter tools. To be able to do that safely and in particularly soft ground conditions, the TBMs are equipped with 2 airlock hyperbaric chambers. These allow the TBM crews to enter into a pressurized environment, as the TBM excavation chambers shall be pressurized. The reason for this pressurized environment is to maintain an appropriate level of pressure within the TBM environment to make sure that stability of the excavation is maintained and to make sure that the groundwater stability is maintained at the same time. This then allows TBM crews to go out into the excavation chamber and the cutter head location, perform whatever essential maintenance is required in a very safe environment for a limited period of time, and then they can then come back out through the TBM, back through the airlocks, and then back out to normal conditions. The very interesting thing about the TBMs that have been adopted for Metro Tunnel is they are slurry shields, what we call mixed shield. This means that there's a continuous circulation of slurry bentonite liquid that runs through pipes that come from the slurry treatment plant, go into the TBM, and then come back to the surface site where the spoil and the rock generated from the TBM excavation process is recycled, separated, and then prepared for disposal to an off-site location. The slurry treatment plant comprises of a filter press unit, desanding units, and large tanks to contain spoil bentonite as well as new bentonite. So the slurry reticulation system itself has got a significant amount of capacity. There's approximately 1,400 cubic meters per hour that is generated through the slurry treatment plant and is pumped to the TBM face. Conversely, then it's pumped back from the TBM back into the slurry treatment plant, and that's where the separation process again is repeated and the slurry is recycled and reused within the TBM operations. In the long term, North Melbourne Station also is a strategic hub for the construction purposes, because after all we have to build the station. The station itself is comprised of a relatively straightforward concrete structure comprising of a base slab, concourse slab and a roof slab. But what's most important here in terms of finishing the station is to make sure that you've got the hearts and the lungs of the station box. That is high voltage, low voltage, the rails, all the mechanical electrical components that are absolutely required for a station to operate efficiently and safely. So just a little bit about North Melbourne station construction itself and some of the challenges and technical aspects we face here. North Melbourne site is geologically quite testing. We've got a lot of softer soils here that we have to both tunnel through, and we've actually excavated through here in the station box. The geological conditions along the Metro Tunnel project are varied, but are predominantly a geotechnical unit that we refer to as Melbourne Formation. The Melbourne Formation is a siltstone sandstone that is generally about 20 MPa in strength. That means it's about half the strength of concrete, so not incredibly hard material to excavate through. We do have some areas of mixed ground conditions, particularly under the Yarra River, which comprises of harder basalt formations and some of the Cood Island silts, which is a sandy clay geological unit. Nevertheless, the tunnelling methods, and particularly the TBMs that have been designed for Metro Tunnel, are more than capable of containing and managing these conditions during the excavation process. To help facilitate those excavation works in a safe and a very well engineered manner, we've got diaphragm walls which were installed and were completed quite a number of months ago. The key thing about the diaphragm wall is that it forms a concrete panel that goes around the perimeter of the station box. These panels create a watertight environment for both the temporary works, as we can see now, with a Stratton System in place which retains the earth and supports the diaphragm wall, but also from a permanent works point of view, where the diaphragm walls itself actually form part of the permanent station structure. So far to date, North Melbourne Station has just about completed the excavation works, with some 160,000 cubic meters of material being taken out and disposed of. Behind me, you can probably see some of the red steel sections. These red steel sections are what we call a Stratton System. The Stratton System is specifically designed to make sure that the forces that are exerted on the diaphragm walls from earth, from water pressure, and from all the plant and equipment that you see around us are able to be accommodated, therefore providing a very safe environment to work with and a very safe structural environment to work within. Thank you very much for joining me on this tour today, and hopefully the talk and the pictures have been insightful. And last but not least, thank you very much to the ladies and gentlemen that participate on this project and work very hard to make it all happen and provide what you see here today. Thank you.